This is the fifth video in our series covering Lie algebras, and today we're going to talk about solvable Lie algebras and nilpotent Lie algebras. But before we do that, I'd like to recall the definition of a derived subalgebra and prove like a preparatory result. So given a Lie algebra L, its derived subalgebra, which we'll denote by L prime, is, well, you can write it setwise as the bracket of L, the whole Lie algebra with itself. But maybe element-wise, it would be the span of everything of the form x comma y, well, bracket x comma y, where x and y range through all of L. So this is like the image of the bracket, if you want to think about it like that. Okay, so our first result will talk about when a quotient Lie algebra is abelian. And what we'll show is that a quotient L mod I, where I is an ideal, is abelian if and only if the derived subalgebra is a subset of I, the ideal. Okay, so this is an if and only if statement, which means we have two things to prove. Let's prove this first direction, this forward direction first. So let's suppose that L mod I is abelian. And let's see where that takes us. Abelian. There we have that. Okay, good. So now what are we trying to do from there? Well, now we'd like to show that everything inside of L prime is actually inside of I. So let's see how we can do this. So let's take some arbitrary thing, I'll call it Z inside of L prime, and let's notice that that means that Z can be written as A1 times the bracket of x1 with y1 added all the way up to an times the bracket of xn with yn with this xi and yi combination coming from L. So notice it's not a single image of the bracket, it's a linear combination of elements of the form, well, bracket something something. And that's because we have this span here. That's required to make it a vector subspace, which is one of the conditions we need in order to have a subalgebra. So now what I'd like to do is maybe push this into L mod I. So let's note that Z plus I, which is an element of L mod I, remember elements of L mod I are cosets, well, this will be equal to A1 x1, y1, all the way up to an, xn, yn, and then plus I. But then by the definition of the bracket inside of the quotient, well, and addition inside of the quotient Lie algebra, we can write this as A1 and then the bracket of x1 plus I with y1 plus I, added all the way up to an and the bracket of xn plus I and yn plus I. Again, this is by the way that we define the addition of cosets and the bracket of cosets within the quotient Lie algebra. But let's recall that we assumed that L mod I was abelian. But L mod I being abelian means that all the brackets are zero. So that tells us that this is zero, and everything in between is zero. So that tells us that the coset Z plus I is the same thing as the coset 0 plus I. But that's the same thing as saying that Z is inside of the ideal I, just by coset equality. But let's see what we have. We started this direction with Z is inside of L prime, and we ended with Z is inside of I. But that's exactly what we need to prove that L prime is a subset of I. So that finishes this forward direction. Now let's move on to the reverse direction. Now for the reverse direction. So let's suppose that we have L prime, the derived subalgebra, is a subset of this ideal. And then what we want to do is show that L mod I is abelian. So how do we do that? So we're going to take two elements of L mod I. So maybe x plus I and y plus I. Those are elements of L mod I. And now, well, we'd like to take their bracket and we'll hopefully get 0. their bracket being 0 would imply that L mod I is abelian. Okay, so let's do that. But in order to do that, let's notice the following. Let's notice that the bracket of x with y is definitely inside of L prime. That's just really a quick follow from the definition of L prime over here. But L prime is a subset of I, just by our assumption. But this element right here, being inside of I, means the coset xy, or bracket xy plus I, is the same thing as the coset 0 plus I. But then, by the way that we define the bracket inside of the Lie algebra, this is the same thing as saying that the bracket of x plus I and y plus I is equal to 0 plus I. But this is exactly what we need for L mod I to be abelian. So is abelian. Okay, good. So that finishes this backwards direction and we're ready to move on. For our next concept, we need to inductively define some ideals of the Lie algebra. And we'll do that as follows. So let's say that L upper 1 with parentheses is equal to L prime, the derived subalgebra. And then L upper n plus 1 with, again, parentheses is the bracket of Ln with itself. In other words, it's the derived subalgebra of Ln. So that's going to give us the following string of ideals. So perhaps it's infinite in that direction, and then we have Ln is a subideal, or it's an ideal of Ln minus 1, so on and so forth, L2, L1, L. And then here's another part of the definition. We say that L is solvable if this truncates somewhere. So in other words, if we've got a natural number n where L upper n with parentheses is 0. Okay, so let's look at some examples. Let's start with the example where L equals GL2F. In other words, it's the Lie algebra of all 2x2 matrices with entries from a field. So let's maybe recall the following fact, which we did in a previous video, and that is that L prime here will be SL2F. So that's pretty easy to check just computationally. And then also L upper 2, well, that's going to be SL2F prime. In other words, the derived subalgebra of SL2F. But we showed that the derived subalgebra of SL2 was SL2. So this is equal to SL2 as well. But then that's going to continue on and on and on. So L upper n will be equal to SL2F for all n bigger than or equal to 2. So that's never equal to 0. I think that's pretty clear because it's always equal to SL2. So that tells us that GL2F and SL2F, if we just start like in the middle somewhere, are not solvable. Because again, the sequence of ideals here never truncates. Okay, well, let's maybe look at another example. So I'm going to reuse the letter L, and now let's say that L is equal to all upper triangular matrices. So A, B, 0, C, where A, B, and C come from our field F. But now what I'd like to do is take a bracket of two arbitrary elements from this to get an idea of what L prime is. So if we need to do bracket A, B, 0, C with X, Y, 0, Z, where X, Y, and Z are from the field as well, well, that's just going to be the product in one order minus the product in the other order. So let's get that calculation going. Okay, so let's see what we get for this. So the product in this order will give us an AX here, and then here we'll have an AY minus a BZ, and then here we'll have a 0, and then here we'll have a CZ. And then from that we need to subtract, well, we get an AX here, and then here we have a BX plus a CY, and I don't know where this minus sign came from, that should be a plus. And then here we have a 0, and here we have a CZ. But let's notice that when we take that difference, the diagonal terms kind of obviously disappear, and we're left with zeros everywhere except above the diagonal where we get something non-zero. And I'm just going to put a star there just because, well, we could do that calculation, but it doesn't really matter. We just need the standard form here. Okay, so that means if L is upper triangular matrices, then L prime is going to be strictly upper triangular matrices. So here we have 0, and then maybe I'll put A, 0, 0, and here A is going to be inside of F. So now let's calculate L upper 2. Well, this is L upper 1 or L prime. It's kind of the same thing. Okay, so now L upper 2. So I'll just do a calculation where I do the bracket of two things inside of L upper 1, because that's how we would calculate what things inside of L upper 2 look like. So here we need to do 0A, 0, 0, bracketed with 0x, 0, 0. So let's see, that's going to be the product in one order. So let's get that written down. Minus the product in the other order. So let's get that written down. Okay, nice. But let's notice that the product of these two matrices is 0. That cancels out. And well, the product of the other two is also 0. So we get 0 minus 0, which is 0. So if the bracket of any two things inside of L upper 1 is 0, then that means that L upper 2 is 0. So in other words, here we have L upper 2 is 0. So let's maybe like put a little box around this to see what we have as the summary. So if L is this Lie algebra, then L upper 1 is this Lie algebra, and L upper 2 is the 0 Lie algebra. So in other words, the sequence truncates, and we do have a solvable Lie algebra in this case. Okay, great. So now let's prove some results about solvable Lie algebra. Now we've got a proposition about solvable Lie algebras, which makes the idea of a solvable Lie algebra look closer to the idea of a solvable group. Whereas this thing over here is not exactly the same as the definition of a solvable group. Okay, so anyway, let's see what we have. So let's suppose we've got a Lie algebra L with ideals I0, I1 up to In, satisfying two conditions. Well, we've got this string, so 0 is equal to In, which is a subset of In minus 1, which is a sub-ideal, I should say, of In minus 2, all the way up to I2 is a sub-ideal of I1, which is an ideal of I0, which is equal to L. So that's our first condition, is that these ideals live in this string. The second condition is for all n between 0 and capital N, the quotient In minus 1 with In is abelian. And if those two are satisfied, then we have a solvable Lie algebra. In other words, that implies that L is solvable. Okay, so let's see how this will go. So by our previous proposition, the only proposition that we've proved so far today, we know the following. We know that if L mod I1 is abelian, then that implies that, let's see, L prime is a subset of I1. Let's recall that, well, that was something that we just proved. And then let's see where this takes us using this result over and over. So I2 mod I1 abelian implies what? That I1 prime is a subset of I2. Okay, good. But now let's see if we can smush these together, and in fact we can. So let's maybe apply the derived subalgebra functor, if you will, to this top thing, and that'll give us L upper 2 is a subset of I1 prime is a subset of I2. So we get something like that. Now let's go one more stage so that we can see what's going on here. So let's see, I3 mod I2 abelian implies, well, what does it imply? It implies that I2 2 prime is a subset of I3. But now let's put these two things together. So this statement right here, and then this thing that we just came up with. So again, we're applying the derived subalgebra functor, if you will. And that'll give us what? Well, that'll give us this L upper 3 is inside of I1 upper 2, which is inside of I2 prime, which is inside of I3. And so now I think it's pretty clear what's going on here. So we can apply induction, or we can like just continue this and see that for all 0 less than or equal to n less than or equal to capital N, we have the following inclusion. L upper n in parentheses is a subset of IN. Okay, good. But now what does that tell us? Let's set lowercase n equal to capital N, and then we have L upper capital N is a subalgebra, or an ideal of I subcapital N, which was equal to 0. But the only thing that's a vector subspace of the 0 vector space is the 0 vector space itself. So that means we have L upper n is equal to 0, which is exactly what we needed, or the condition that we needed for L to be solvable. So we've got it. All right, let's do another result. A couple more general results regarding solvability. So let's start with the pretty quick one. So let's suppose that L is a Lie algebra and K is a subalgebra. Then L solvable implies K solvable. So if L is a solvable Lie algebra, then K is also a solvable Lie algebra. Okay, well, how might we do this? Well, let's notice that the derived subalgebra of K is going to be, well, that's equal to the bracket of K with itself, which is pretty clearly a subalgebra of the bracket of L with itself, which is equal to the derived subalgebra of L. And then kind of inductively following this, we get the K upper n as a subalgebra of L upper n. So notice that we can take, or maybe we can find some natural number n such that L upper n is equal to 0, which means that we have K upper n is a subset of L upper n, which is 0. But that tells us that K upper n is itself equal to 0, but that's exactly what we needed for K to be solvable. Let's move on. Okay, for our next result, we've got a Lie algebra L and an ideal I, and we'll show that if the ideal is solvable and the corresponding quotient Lie algebra is solvable, then the parent Lie algebra is solvable. Okay, so let's see how we might do this. So this starts with a little bit of a result about these kind of upper n objects for a quotient Lie algebra. And it goes something like this. So we claim that L mod I upper n is equal to L upper n plus I mod I. Okay, nice. So that has the effect of somehow like distributing this upper n onto the quotient, if you will. And we're gonna prove this by induction. And so for our base case, let's maybe take the case when n is equal to 0. And let's start on this right-hand side. So we have L plus I mod I, because upper 0 is just the parent Lie algebra. But then by the isomorphism theorem, I think it's the second isomorphism theorem, this is isomorphic to L mod L intersect I. But since I is an ideal of L, L intersect I is simply I. So this is L mod I. But then since this object is kind of naturally a subset of this object, the isomorphism is actually equality. So there we have our base case. So now let's make an induction hypothesis. So let's suppose for some K bigger than or equal to 0, we have this result holding here. So we have L mod I upper K is equal to L upper K plus I mod I. And then from there, we want to consider the next case. So in other words, we're going to consider L mod I upper k plus 1. And hopefully we can write it as, well, what we need to on the right-hand side. Okay, so let's notice by definition, this is going to be L mod I upper k and then prime. Well, that's how we're defining these things over here. But now let's maybe apply the induction hypothesis to the inside. So that'll leave us with L upper k plus I mod I, and then we have prime. But then let's apply the induction hypothesis to that. So that's going to give us L upper k plus 1, because that's the same thing as L upper k prime, and then plus I prime plus I. And then this is all mod I. But next up, we know that I prime is a subset of I. So that means that we can just absorb this I prime inside of I, meaning that we have this is equal to L upper k plus 1 plus I mod I as needed. Okay, so there we have it. We've proven the claim and we're ready to look at the result. Okay, so here's the little subclaim that we proved, and now we're ready to show that if these two are solvable, then our parent subalgebra is solvable. Okay, so let's maybe take two natural numbers. I'll call them capital M and capital N, such that, well, they're going to be the natural numbers associated to the solvability of I and L mod I. So this M is going to be associated to the solvability of I. So in other words, that means I upper M is equal to 0. And then the N will be connected to the solvability of L mod I. So that means we have L mod I upper N is equal to 0. Okay, good. So now where do we want to go from there? Well, let's start with this one and see where we get. So we've got 0 is equal to L mod I upper N. But, well, we proved this result, so that means we probably want to use that result. So that means that this is equal to L upper N plus I mod I. But then if this is the 0 Lie algebra, well, that's only possible if L upper N plus I is a subset of I. So let's write that down. So this means that L upper N plus I is a subset of I. That's how you form a 0 quotient, is if your so-called numerator is a subset of the denominator. Now, I'm putting those in quotes there. But notice that this I is equal to this I, so this really means that L upper N is a subset of I. So let's write that down. So L upper N is a sub-object of I. So now what we'll do is maybe quote-unquote upper M both sides of this. So in other words, we'll take the derived subalgebra action M times. So that tells us that L upper N upper M is a subset of I upper M, which itself is equal to 0. But then we'll have a homework exercise that proves that this is L upper M plus N. So that will, in the end, leave us with L upper M plus N is equal to 0, which is exactly what we need for L to be solvable. Okay, let's move on. So our next result involves two ideals. So again, we've got a Lie algebra L, but now we've got ideals I and J. And we'll show if both I and J are solvable, then I plus J is solvable. Okay, so let's take the maybe solvability numbers for I and J. So here we'll have M and N, natural numbers, such that I upper M equals J upper N equals 0. So again, they're the solvability numbers, if you will. So now we're going to use a combination of something we proved in the previous part, as well as the second isomorphism theorem. So let's look at this. We've got I plus J mod J upper M. Okay, so first off, we can use the second isomorphism theorem on the inside here to show that this is equal to I mod I intersect J, now upper M. And then we can use that claim that we had on the previous proposition, or on the inside of this previous proposition, to say that this is I upper M plus I intersect J mod I intersect J. Okay, good. But then I upper M is 0, so this is simply equal to I intersect J mod itself. But any Lie algebra mod itself is going to be the 0 Lie algebra. So that proves that this I plus J mod J upper M is 0. Okay, but then also we know that J is solvable. So I guess we didn't use the solvability number for J. So anyway, let's see what we have. So we've got the quotient is solvable. Well, let's write that down. So we have I plus J mod J is solvable. And we also know that J is solvable. Okay, so those are the two things that we know. But anytime we know that the quotient is solvable and the ideal that we're quotienting by is solvable, then the Lie algebra on top is also solvable. That was exactly the previous proposition. So that gives us I plus J solvable as needed. Okay, so now let's move on. So our next result involves a really important device attached to Lie algebras known as the radical. So here's the proposition, which we'll actually build a definition over here. So given a finite dimensional Lie algebra L, there is a unique solvable ideal containing every other solvable ideal of L. And that unique solvable ideal is called the radical of L, which we'll call rad L like this. So let's maybe see how this proof goes. So let's consider the following set. So I'll call it maybe script C, and it'll be equal to all ideals I of L such that they are solvable. So I is a solvable ideal. And then next up, what we want to do is use the fact that we've got, well, a finite dimensional vector space here. So let's take R, which is an element of C, such that the dimension of I is less than or equal to the dimension of R for all I in C. So in other words, it is an element of C with the maximum dimension. And notice the ability to get something with maximum dimension is only possible because we have a finite dimensional Lie algebra. So that's where we use that. So next up, let's notice for all I in C, we have the following. So we have R is a subset or a subspace of R plus I. So that's just simple like vector space stuff. But then that means that the dimension of R is less than or equal to the dimension of R plus I. But then also we know that R plus I is solvable. And we know that R plus I is solvable by the previous result. So that means that its dimension is less than or equal to the dimension of R. So this is less than or equal to the dimension of R. But what does that mean? That means that we have equality of dimensions here because we've pinned the dimension of R plus I between two copies of the dimension of R. So here we have this is the dimension of R. But that's only possible if I is a subspace of R. Okay, so that shows that R contains every solvable ideal, but it doesn't show that it's unique, but it's actually pretty easy to show that it's unique. So any other R prime that achieves the maximum dimension will be such that R prime is a subset of R and R is a subset of R prime. But that means that they have to be the same. And that's by this condition right here, just doing these kind of two things in reverse. One where R prime is playing the role of the maximum dimension and one where R is. But then if those two inclusions are true, then they have to be the same. But them being the same is exactly what we need for uniqueness. So there we have it. This shows that R contains all solvable ideals, and then this argument right here with the words that I said to fill in prove that that is unique. Now we're going to build a couple of new definitions off of the radical. So, well, the first isn't built off of the definition of a radical. It's kind of ported over from something that we might have learned about in group theory, and that's the notion of simplicity. So we say a non-abelian Lie algebra L is simple if it has no non-trivial ideals. So recall a group is simple if it has no non-trivial subgroup. But we require to have a non-abelian Lie algebra here. So abelian Lie algebras cannot be considered simple. Okay, so next up we say that a Lie algebra L is semisimple if its radical is 0. But that's equivalent to saying that it has no non-trivial solvable ideals. Recall that the radical contains all of the solvable ideals. So if the radical is 0, then it can't contain anything. Okay, so now let's look at a nice result. It says that if we've got a Lie algebra L, then L mod the radical of L is semisimple. So let's notice that ideals of L mod the radical of L are of the form I mod the radical of L, where, let's see, the radical of L is contained in I. So this is by like a correspondence theorem for ideals like inside of the quotient and ideals outside of the quotient, which is similar to something you learn about in ring theory. I don't think we proved it, but the statement and the proof are really similar to what you might see in ring theory or in group theory. Okay, great. So now let's suppose that we have a solvable ideal and see that something goes wrong. So let's suppose, like I said, that I mod the radical of L is solvable. But then let's gather some stuff that we know. So we know, first of all, that the radical of L is solvable, kind of by definition. And then we also know that I mod the radical of L is solvable. That's because we've supposed that we have a solvable ideal of L mod the radical of L. But then by our previous result, if the quote-unquote denominator is solvable and the whole thing is solvable, then the parent Lie algebra, in this case I, is solvable. So this is going to, like I said, imply that I is solvable. Okay, but I being solvable means that it's contained inside of the radical of L. Recall that the radical of L contains all of the solvable ideals. So let's see, we've got I is in the radical of L. But let's also recall by our correspondence, the radical of L is contained inside of I. But that means that I is equal to the radical of L. Okay, but that means that I mod the radical of L is equal to 0. So let's see what we've done. We supposed that we had a solvable ideal and we ended up with, oh, that solvable ideal is actually the 0 ideal. But that's exactly what we needed to do to show that L mod the radical ideal is semisimple given this definition over here. Okay, let's move on. Now we're going to quickly look at the notion of a nilpotent Lie algebra. So that's going to require us to define another sequence of ideals. And so these are sometimes called the lower central series, whereas the other ones were the upper central series. So given a Lie algebra L, we'll inductively define L upper 1, where we don't have parentheses, as L prime, the derived subalgebra, and then L upper n plus 1 as the bracket of L with Ln. And then we'll say that L is nilpotent if L upper n is equal to 0 for some natural number n, where we don't have parentheses here. That's the difference in the notation. And now we're going to finish the video with the following result, and that is if we've got a Lie algebra L and L mod the center of L is nilpotent, then that implies that L is nilpotent. And we're going to start this off with a claim that's pretty similar to one that we used in a previous proposition, and that is the following. So L mod ZL upper n without parentheses is equal to L upper n plus ZL mod ZL. Okay, great. So that allows us to like bring the upper n inside. And now I'm maybe not gonna prove this. I'll leave this as a homework exercise. I think it's pretty easy to do either element-wise or maybe similar to what I did before. So now let's see where that takes us. So if L mod ZL is nilpotent, then we have something that I'll call capital N such that 0 is equal to L mod ZL upper capital N, or like, yeah, upper capital N, where that's outside of parentheses. But now we'll apply this claim to turn this into L upper N plus ZL mod ZL. Okay, great. But let's notice that this being equal to 0 tells us that L upper N without parentheses is a subset of ZL. Okay, nice. And now we're pretty much home free. Let's look at L upper N plus 1, which is defined to be L bracketed with L upper N. But then since L upper N is a subset of the center, then that means this whole thing is a subset of L bracketed with the center. But anything bracketed with the center is going to give us 0. So there we have it. We have L upper N plus 1 is equal to 0, which is what we needed to show that this was nilpotent. Okay, I'll leave you with some exercises. Here are some exercises based on what we just saw. So the first is to show that all strictly upper triangular 3x3 matrices form a nilpotent Lie algebra. Next is to show that L upper M, all upper N, where those are in parentheses, is equal to L upper M plus N. So we use that in a proof. Next up, show that every nilpotent Lie algebra is solvable, and then give an example of a solvable Lie algebra that is not nilpotent. Finally, let's consider the Lie algebra of 4x4 matrices defined by A, B, C minus A in the upper 2x2 block, and x, y, z minus x in the lower right 2x2 block, and zeros on the off blocks, where a, b, c, x, y, z are come from the field. And then show that that Lie algebra is semi-simple but not simple. And that's a good place to stop.